Pedigrees are a really useful tool used by genetic counselors quite often that show relatedness among members of a family. So, showing how people are related to one another, and then you can use that to track specific genetic conditions. So, when we're talking about pedigrees, the most important thing to remember is that squares represent males and circles represent females. And then a horizontal line between a male and a female represents that they have children, okay, which is represented by a vertical line down. Siblings are connected to one another via their parents by this vertical line. Notice they're not connected to each other this way. That would be bad because that would be incestuous, not good. And then based on how these boxes and circles are shaded in, that shows you the inheritance. So basically, how a pedigree works, let's say this is me, okay? Here's my husband, here's our son. Okay? Now, if I want to put in my parents, here's my mom, here's my dad. Okay, so now, right now we have 3 generations showing myself. I'm going to draw an arrow to myself because I'm the proband. I'm the one that's this pedigree is focused on. And then you can see my son. I'm an only child. I don't have any siblings. Okay. My father, on the other hand, was one of 5. Okay. He had 2 older sisters and 2 older brothers. Okay. And then I can put my grandparents up here too. Okay, so those are my dad's grandparents. My mother was one of 4. Her side gets a little bit more complicated. So she had 2 sisters and a brother. Here's her father and her mother. But my mom's mom died when my mom was quite young, so her father got remarried. And he and his second wife, fit them over here, had 3 more children. Okay, 2 boys and a girl. So now we can see in this row all of my uncles and aunts and my parents, okay? And then up here, grandparents. Okay? And then it could get much more complicated if we started putting in aunts and uncles by marriage and my cousins, etc., but we're not going to do that. But you get the idea of how we can see generations. And oftentimes generations are labeled, I'll do it over on the right-hand side because I have a little more room, with Roman numerals. So 1, 2, 3, and then Liam would be the 4th generation down here. So if you ever see Roman numerals, those are referring to generations. And then sometimes people within each generation might be labeled going across like that. So if I refer to individual Chu, that means I'm referring to this person right here, okay, my aunt. If I was referring to individual 3-1, that's 3rd generation, individual 1, that's me. Pedigrees become really useful when you're looking at traits. So this is an autosomal dominant pedigree for Huntington's disease. Huntington's disease is something, if you ever watched House, which maybe you guys are too young for House now, but one of the characters had the trait for Huntington's disease. Huntington's is dominant, so you only have 1 copy of the allele, and you'll have that phenotype. So we could put in people's genotype. So anybody who is recessive, okay, not shaded in with Huntington's in this case, we know that they don't have the allele at all. Okay, so they would be homozygous recessive. And then anybody who has Huntington's, who is shaded in, has 1 copy. Now, important things to notice about autosomal dominant traits is that they don't skip generations. So Huntington's, in this case, shows up in each generation. It can only be passed on if you receive the allele from one of your parents. Okay, so that's very important to keep in mind. Here we have an autosomal recessive pedigree. So this could be for something like cystic fibrosis, which means you need to have 2 of the recessive alleles to inherit the trait. I'm going to use the letter A just because it's easier to show. So we could start with everybody who is shaded in and has this trait we'll put two little a's, okay, because the only way they could exhibit that would be to have two recessive copies of the allele. Now, everyone else that doesn't have the trait, we could at least put in a dominant allele because they are not affected, so they must have a dominant allele. Okay. Once you do all of that, then you can start to figure out, okay, so what other clues are there to figure out that second allele for those people who are dominant? So if we look at individual, let's start with individual 3. Okay, so here's a person not affected, married someone who is affected. They have 4 children. 2 are not affected, but 2 are. So if we look, these children who are affected, right, received one recessive allele from their mother. The other recessive allele must have come from their father. So individual 3, this male, must be heterozygous. Okay? We can, if we stick within the same family, individuals 9 and 12, right, receive the dominant allele from their father. Their mother can only give them a recessive allele, so they also must be heterozygous. Okay? If we look at individual 14, we could say the same thing, right? Because individual 14, her mother is affected, so she must be as well. And after that, we can't really figure out too much. There's a good indication that individual 2, because these people, none of their children are affected, that individual 2 might be homozygous dominant, but we aren't positive. We can say, actually, that individuals 6, 7, and 8, 1 and 2, their children, all must be heterozygous because their father is affected. Right? So they're all heterozygous. And then individuals 15 and 16, okay, down here, we can't determine their genotypes either because they could be homozygous dominant or heterozygous. Maybe if they had children someday, we would be able to learn a little bit more. Of course, there's also genetic testing, which can tell us a lot about these things too. But we can determine all of this just by looking at a pedigree. Something else to consider when you're looking at pedigrees, if you see a situation like this, if we just look at this immediate family, where the trait seems to be skipping a generation and that it doesn't appear in the parents, but it does appear in one of the children, one of the offspring, that means it's recessive, okay? Dominant traits cannot skip a generation, recessive traits can. Another indication that this is a recessive trait is when both parents are affected, all of the offspring also have to be affected because they only have recessive alleles to pass on. The final pedigree we're going to look at is one for colorblindness, which remember is an X-linked recessive trait. What makes this pedigree different from the other one that we just looked at is this one actually shows the carriers. So all of these circles that are half shaded in, those are all represent females who have one recessive allele for color blindness on the X chromosome, but they still have that dominant allele as well. So they're not actually colorblind, right? So this man who is colorblind, right, we would know has that recessive allele. We can see that showing up in a few places with our men. And then you can also see here we have a colorblind daughter who received a recessive allele from her mother and from her father. But most often, when we're looking at recessive X-linked traits, it appears much more often in men than in women, and it tends to be passed on through the mother as well. So if we look, here's a father who passed on to his daughter, kind of skips a generation, right? None of his children are colorblind, but then she has a son who's colorblind. She has a daughter who's a carrier, and then she has a son who's colorblind. So it's not being inherited from the father, but from the mother. We'll be looking at these different types of pedigrees in class.